principles of fairness. But if somebody looked at it differently, but I don't want to answer it online. Anyhow, thanks for letting me know. There seems to be bug between the two courses because anyhow, any other question with respect to the homework? Perfect. We will continue with hashing, plenty of hashing. Definitely showing things that are different from the book. So the textbook is still very good references, but remember that after that you have to go back to the slides and ask what else did I cover. And the good thing about watching the lecture, by the way, if you didn't notice, both on D2L and on Pinapto and on Twitch, you can change the speed of the way I speak only by a factor of 2, so it only helps you this much, but you can definitely fast forward for what I'm saying. Okay, I wanted to go back to the 3 variants of the multiplication method. By the way, anybody has an idea how to make my iPad completely silent? Do you hear it in the background, or you guys don't care?
I haven't heard of it.
Okay, perfect. Okay, why with minimum volume it still makes noises? I'm not sure. Okay, the 3 variants of multiplication. We wanted to start with h of k is just k modulo m. We can do it. What's the problem with this? What's the problem is just use h of k equals k mod m. Many things can go wrong. For example, the numbers k's are only even and m is even as well. Then we never place things in the table which are...
Fix your camera so we can see the whole whiteboard. Thank you.
Okay. By the way, kudos to OBS that makes this nice arrangement of cameras and things on the screen work so cool. K is even, happens to be that all your keys are even, and the table, the size of the table is even as well. What's wrong with this? That we never place things in the table at odd cells. Cell number 1 will never insert anything to it. That's one problem. Here is another problem. Let's say that the K or the keys are 3, 7, all of them, a lot of keys, but all are larger than 1,000, while M is 2,000. What happens? I have plenty of keys that only fill up one part of the table, and all the cells from 1001 all the way to 2000 will never be occupied. So another bad thing that can happen if you are using k modulo m directly. Another thing that could be that could go wrong, we talked about it. If m is a factor of 10 or m is a factor of 2, and some behavior of the data implies that we are using the last digits as a control group. For example, not control group, control number, saying whether you are at this department or this department depending on the last digit. That is that there is no real variability in the data. When I look at the keys, 1, 2, 3, 4, 5, 3, 7, 2, 4, 5, 9, 4, 2, 1, 5. All these keys are different than each other, but they all have the same last digit. That's why we wanted that two keys that are different, no matter where they are different, if it's in the first digit, the last digit, whatever, we want them to give them a chance at least to fall into different cells. And the three methods that I didn't really distinguish between them, and the textbook doesn't really distinguish between them either, is that are all around the multiplication method. All starts by, let's take the key k and multiply by a number a, and the number that we might get is of course larger than the size of the table, so we still end up by modulo m, always, because we want an integer between 0 and m minus 1, and that's what modulo is doing. However, let's multiply it by some number and maybe do some other operation. And which number should it be? There are a few variants, and I want to go over a few. So one variant will say pick a, this number, as a strange constant. Not necessarily, and actually with a lot of digits after the decimal point. A equals square root of 2 will do just fine. A equal E will do just fine. And now look at what I'm doing here. That wasn't on the slide last class. I multiply A by K, and I multiply A by K once again, and this time I take the floor. That's A times K, that's A times K for floor. What happens in the red parentheses? What happens when I take the difference between these two numbers? Let's think that AK equals 3.1415. If this is A times K, what do I get in the red parentheses?
Should give you a number between 0 and 1.
It takes the this number, the floor of this number is of course just 3. This minus 3 gives me 1.1415, and so on. And here all the digits participate, and this is a number between 0 and 1. So I multiply it by m. It now becomes a number between 0 and m. A number m times this is a number between 0 and m, but it's a float. Might be a non-integer, that's why I take the floor once again of this number, and that gives me a legit index. Then I can go to the table and use this value as a normal index. And again, all the digits of k might participate, might contribute. That is two keys that are different in any digit, even if it's the first digit, even if it's the last digit, it might leads to different value, likely to lead with a different value. Okay, the second multiplication method says, let's take a as a large integer. Let's take a as the key as before. Let's multiply them. But modulo 2 directly, if I take modulo 2, what do I get? Only the last digit. So I'll get a number between 0 and 1, which is just the last digit. So that takes into expression only the last digit of the key. Right? If I'll change this digit of the key, but not this one, the last digit of the result will not change one bit. It's also not a great idea to take the first digit. What should I do? I'll take a few digits in the middle. How many digits in the middle should I take? Just as much to give me an index between in the size of the table. Right? If the table is of size 16, then I need 4 digits. Then I'll take 4 digits somewhere in the middle. Table is of size 32, I need 5 digits somewhere in the middle. Hacking question or C question. How can I take the first 3 digits? If I want the rightmost 3 digits, what should I do? So so far I'm not using this intuition of taking it from the middle. I just want the rightmost 3 digits. Then I'll take AK modulo 8, right? Or as we discussed last meeting, do AK and bitwise AND with a 7, because 7 is 0, 0, 0, 1, 1, 1, it's end. Okay, that was for the, if I want the rightmost 3 bits. How can I take the 3 bits, but let's say the bits, these 3 bits of the result? If this number is X, how can I generate from X the number which is represented by bit, not bit 0, bit 1, 2, and 3? When I'm doing the modulo operation, I'm killing everything to the left. But how can I get rid of this one? Hacking question? Sorry?
Bit shifting?
Bit shifting.
You bit shifted over
Yeah,
to the right ones?
exactly. You're doing RSH, if I'm right, right shift by 1 bit and taking of X and taking the result and do now modulo 8. So the right shift just take all the bits and move them 1 element to the right, killing this one, and then the bits to the left you're killing by doing modulo. Similarly, you can take the number of bits that you want just from the middle. I'm skipping the technical details. I don't think that's a overall public. If you need them, you'll find it in the textbook or in different slides. Okay, we have it. We talked about why the multiplication method is working, because it says that if I change the key by any amount, I'm just adding to the key and multiply by A. It means that I take the old key, some place that I landed in the table, and let's say that I'm adding A to it. It takes me to some, after the modulo 8, of course, it takes me to some different and seemingly unrelated place in the table, especially if A and K are relatively prime to each other. That is that A is 7 and M especially is prime. And if you don't know what to answer in the exam or in future exams, how should we pick the size of the table? Just try to say as many times as you could prime, because it usually helps. And one advantage of all these 3 methods, as together with the normal just takes the modulo method that we started from without multiplication by A, is one property that is easy to forget. I want to be able to compute age of k quickly. It's not something that I need to spend a lot of time doing it. It's something that I am doing for a lot of keys and shouldn't slow down my algorithm. Right. So in this aspect, our hashing is quite different than hashing in cryptography, where computational time is still a factor, but it's far from being the key factor. Here, of course, I do want to be able to compute age of k very fast. I don't want to look at any tables. I don't want to look at any auxiliary data. I want to look at a constant and do very simple operation. Bit shift is nice. Bit end is nice. Multiplication, slightly less nice, but still tolerable. It's trying to discourage you from looking for a very efficient hash function that is very efficient for the data, but also takes a lot of time to think about it. I'll talk about it more later when I'll talk about perfect hash function. And another round. Okay, another slide that I want to discuss a bit further is the slide of, what is so small? Is a slide of, can I make this thing a bit larger? I guess not, at least not in real time. Is how are we using hash functions for distributed data structures or for data robustness. So let's think about the following case. We want to store a lot of records, and as you remember in all our discussion about hashing, or in all our discussion about data structure in general, excuse me, all our discussion about data structure in general, our data record, we have a record, and a record contains, say, the student ID, and the record also contains the the student details. Where is the student living? What was the grades that he or she got, and so on and so forth, all the many details that we have over here, and then we have the key. So the remaining data are all the auxiliary, all the satellite or auxiliary data. So let's think about this scenario once again, and let's think about the following case. We have a set of, let's say, 8 hard drives, sorry, plural. Maybe they are separated, maybe they each sit on one of the users, and there are 8 different users or n different computing centers. Maybe they are all sitting inside such a device called a RAID, which is a set of several disks put together. Sometimes they all have the same axis and they share pieces of hardware. Sometimes they are really separate from each other. Anyhow, we have a set of 8 hard drives. Let's label them 0, ... all the way up to 7. So 8 cells, just similar to the cubby that we have earlier. And I want to use them even though each one is likely or with some probability might fail. Maybe it's not turned on, maybe it's not online. Still, I want to be able to access my data. So I cannot take a record, each individual record, and store it only on a single hard drive. That would be a bad idea, because once this hard drive fails, then this data is lost, temporarily or permanently, but this data is lost. So what should I do instead? If I don't want to be depending on a single hard drive, I need to store each record on more than one hard drive. Let's arbitrarily say I want to be able to work as long as no more than 2 hard drive fails. That is, I want to have robustness against failure of 1 or 2 hard drives, still be able to access all my data. If 3 hard drive fails, then okay, it's too expensive for me. Too expensive to handle this case as well. But as long as no more than 2 handles, I'm still okay. So I want robustness against disk failure. Now, at the same time, I want to have a load fairness. That is, the number of records and the number of records that I'm going to store is going to be quite large. If I don't care about redundancy at all, if I don't care about robustness, then I'll say each record will be only in 1 hard drive, so each hard drive stores n/8. Now I want every record to be stored in 3 hard drives, so each one of the hard drives should approximately store 3n/8. And if I would have known ahead of time what are all the keys, who are the students, maybe I could hit this number exactly. Each hard drive stores exactly 3n/8. But this is not the case. I don't know ahead of time who are these disks, so who are the records that I'm going to store. That's why I need the help of a good hash function. So what's the operation that I need to have? Once a new record with a key k appears, I need to be able to insert it, and I want to efficiently decide where I'm going to insert it, which hard drive. I want to supposedly also delete it, and mostly to be able to find this record. The student just appeared, this credit card just appeared. I need to be able to access this data on at least one of the places that stores this data. And what I don't know ahead of time is who are the records that are going to appear, what IDs that I'm going to appear. And I want to show you how cool it is to use hash functions for it. And I'm not discussing now how I arrange the data inside the hard drive. It's orthogonal question. I'm just asking for each number k, each key k, on which hard drives do I store it. So I need to pick now 3 hash functions in plural. I'll call them age1 of k, age2 of k, and age3 of k. 3 hash functions. Let's, in this simple example, define them by age of k is just age I of k. The I is either 1 or 2 or 3. I'll just get it by taking different constant ai times k, and we always end up by doing modulo m. M here in this example, my m is 8. So I'll go further with this example. My first constant will be 3. So a1 is 3. My first function age1 is 3k mod m. My second constant is 5. My third constant is 7. And now I decide how to insert a new key. So I'm computing age1 of k. In the little examples that I created, assume k is 15. Age1 of k is 3 times k modulo 8. 3 times 15 modulo 8 is 45. 3 times 15 modulo 8 is 5. So that tells me that I need to store this record in disk 5. What's the cool thing about the hash function is that if the keys are random enough, or at least not designed by some vicious adversary, then the chance that I'll store this record in disk 5 is similar to the chance that I'll store it in disk 4 or 3 or 2 or 0. Each disk has the same probability to be hit if my hash functions work well. However, I said that I'll store it in 3 disks, so I'll also compute what is, we said k equal 15, I'll compute 5 times 15 modulo 8, whatever number it is, that's the other hard drive that I store it, and 7k modulo 8 will be the third hard drive. And what am I trying to avoid? Once you tell me to search K, to find K, I'm not going to bug each one of the hard drives by asking you, do you have K? Do you have K? Do you have K? Because then if I have a lot of queries, it will take a lot of effort from each one of the hard drives. Instead, you want to ask me, are you storing the record of K? My access will be computing what is age 1 of k. I still know what is age 1 of k, 3 times k modulo 5, disk 5, meaning that disk 5 is the first one that I'll search for this record. If I don't find it, maybe it was never stored, or maybe it was maybe the disk itself crashed at the meantime, I don't know. If I don't find it here, then my next attempt to find this key will be in disk age 2 of k. If I don't find it there, I'll try age 3 of k. If I don't find it there, then I'll say maybe it was such a critical crash that deleted it completely, or maybe k was never exist in my data structure. Cool. And I'm only taking effort, the only disks that need to worry about this query is only these 3 disks out of the 8 or out of the 100 or 1,000 or million of users of PyParper held in mind. Not everybody needs to be bothered by each separate queries, and see how well it fits distributed data structures. If now I mentioned it as me as a server that decides where do I store everything as a mighty server, but essentially the way that it works is completely autonomous. The only thing that a leader server needs to do is to decide what are the hash functions and distribute the hash functions to all the users. Distributed system completely. And now when everybody knows what are the hash functions, every piece of the network can work completely autonomously. There is no need of any specific data structures that will know where each record is stored in this big storage place. So I think that that's one of the coolest applications of hash functions that I'm aware of. Questions about it? Okay, let's bug you with a little question. Instead of asking it in the homework, let's ask it now and get you into group and ask you this question. I'll first write it in using the whole glory of formalization to confuse everybody, and then I'll give an example where it's much simpler. I'm using part of the techniques of active learnings of dividing you into groups and ask you questions. What I'm not planning to do is to call names and to force you to answer, because I think that the class should still stay a safe place. I mean, you should not be online because you'll be concerned to be called and be embarrassed. You are still volunteered to participate. Okay, here is a formal way to describe it, and then I'll explain. Let U is a set of all the possible students that might appear to the university. And possible set of all the students that might appear to the university, and let's assume that the universe contains at least m square many keys. M is always the size of the hash table in this chapter. Age is any hash function. I thought that I'm very clever, so I took my time and decided about the best constant that I can come up with, the best algorithm I can come up with. I put all my effort and I designed age, the hash function, to be really clever. But there is still one thing that I don't know, which are who are the students that are going to come to the university. All I know is from which site they are, what the numbers looks like, but I don't know who they are actually. However, age is really clever. And to take some concrete numbers, let's assume that m square is, let's use a different color. M square is 100. So I'm going to, there are at least 100 people that might appear at the university. Age is a hash function. Age of k is a number between 0 and m in this case will be 9. So age is some cell in the hash table, and the hash table contains 10 cells. M equals 10 in my example. However, the adversary, if there is any spelling mistake, please fix. The adversary, somebody that you step on his toes at some point, and he's trying to get your data structure to behave as badly as possible. He can decide who will be the set K of students. K are the students that are actually coming. He'll decide which ideas are actually coming. He will tell you, I can pick a set of 10 students from this group of 100 students that you started from, such that what are we trying to get with the hash function? We are trying to say that two keys, as long as they are different, we hope that they'll fall in different cells. What is this happens? The age of K1, two keys K1, and age of K2 equal, meaning that we have a collision. The adversary claims that he can always, or she can always pick a set of 10 keys from the universe, such that not only that there are collisions, but everybody collides with everybody else. That is, when you think about the hash table over here, then in the hash table, if I solve collisions by chaining, then in the hash table, I will only have one cell, and in this cell, there will be 10 students, and no other cells will be occupied. In other words, no matter how clever your hash function is, there are always nasty examples that will say there are still collisions despite all your attempts. Provided, of course, that you first decided about the hash table. The adversary knows what's a hash table. The adversary knows what you are using, and then the adversary can have the choice who is coming to the university. Is the question clear to everybody? A bit more mathy, a bit more combinatorically. I want to say, no matter how hard you worked on age, the adversary from this group of 100 students will pick, this group of 100 students can always pick 10 of them, such that the hash function will send all of them into one bucket. And let's divide you into groups. Yeah. Okay, let's collect you. So the two rooms that I visited got it right, that it's just a simple implementation of the pigeonhole principle. Because what you're saying, what the adversary is going to do, what the adversary is planning to do is to say, I'm going to take a set of U of whose cardinality is m squared. There are m square items in the universe, and I'm going to, let's call them K1 all the way up to KR, all these guys, and I'm going to compute what is age of K1 and age of K2, all the potential students, all the way up to age of KR, and I'll see who is falling in cell number 1. Maybe there are only 2 students that fall in cell number 1. Who is falling in cell number 2? Maybe there is only 1 student. Who is falling in cell 9? Nobody. However, could it be that none of the cells, that each one of the cells contains less than 9 students? Could it be that each one of the cells contained less than 9 students? Well, this cannot happen. That's just a pigeonhole principle. And the reason that it happens is that how many students, each one of the m square of the 100 students is mapped to one of the cells. So altogether there are 10 cells to which we mapped 100 students. If each one contains less or equal than 9 students, then altogether I have room to only 90 students. Well, I said that I have 100. So one of the cells should contain at least 10 students, and now the adversary will say, okay, great. The cell that contains 10 students, these are exactly the students that I'm going to send to the university to prove to you that all your attempts to generate a good hash functions are for nothing, and there is still mean lower bound. Make sense? So it's a good example because it convinced you that you can come up with good hash functions. You can come up with perfect hash functions, but only if you know the data ahead of time. Otherwise, collisions will happen. The best we can do is to hope that there are not a lot of collisions, but collisions might happen. Let's talk about the dot product method. Somehow, I'm teaching this course, many times. And somehow this is a subtopic that people find harder. So I try to use different slides to and more examples to express what is a dot product method. So first, what is a problem that we are trying to answer? Keys that the examples of the keys that we saw so far were friendly numbers, not too large. 15, 100, all the keys were very small. It's very rarely the case, even for student ID, it's rarely the case. It's the decimal number with 20-something digits. But in general, storing values based on keys only is only one of the applications of hash function and not necessarily the important one. You want to essentially hash many other items. You want to hash very long keys, for example, documents. You want to hash musical records. You want to hash books. You want to hash images, DNAs, samples, geometric structures. To do face recognition for good or for bad, to store patterns of malwares or viruses, etc., etc. Fingerprints, all of these things could be hashed and should be hashed so that if I'll put my finger or print, it will be easy to see if I'm in the database or not. But and hashing is extremely powerful in working on these shapes, except that now the keys are long. There are lots and lots of numbers in the keys, so we need different ideas. We cannot just take the key as a small number, multiply it by a constant, and do the modulo. I mean, we can, but for this we need to take the key and make it a number, a single number first, and these numbers will be huge. If I want to store images, so TinEye and Google Images Search will work properly, making it into a number and making manipulation of these numbers is extremely expensive. What's my hope is, just as before, I want that age of k could be computed fast. Fast meaning like if it's a big document, big video, I want to make one pass on this video, not multiple passes. So I still want to make numbers out of it, but not a single number. That's where the dot product is going to be so useful. And it's really one of the important concepts here. I am not going to have a single key. What I'm going to do is to take the key, which is a very long number or very long binary string, and I'm going to break it into several numbers. I'm going to think about it as a vector or an order list of numbers. And I need to adapt it to my hash function. So instead of just using one constant a and apply age of k equal k times a, now I have a lot of pieces of the key, So I need a few constants, and I'll tell you how to pick them, how to generate them, but I'll need possibly a long sequence of constant. Let's call them A1, A2, A3, A4. These are all constants that I need to remember. Quick example. I want to store alphabetic strings, uh, uh, strings of 4 letters, and this is a key, BDCZ will be one of the keys that I want to store. And what I'm planning to do is not to make it into one big number. It will be too large for me. Instead, I'll pick four constants, A1, A2, A3, A4, and I'll take the first letter of the key, B. Its ASCII value is 66. Take 66, multiplies by A1. Take the next key, D. Its ASCII value is 68, multiplies by A2. Similarly for A3, similarly for A4. Take all these keys, sum them up, all these values, sum them up. You're getting a number that is too large. So you'll do modulo m, as always, to get a number between 0 and m minus 1. That is, the big idea right now was just not multiplication of one key, but break it into several characters, several keys, and multiply each one by a different constant. Why I prefer to have different constants right here instead of just doing, of course, I can take this key BDCZ and make a number out of it, which would be K will be the ASCII value of B plus the ASCII value of D plus the ASCII value of C plus the ASCII value of Z. But what happened here? Well, I said that I always have collisions, but at least I'm trying to make collisions more rare. And if my key is B, C, D, Z, that is, I just take a permutation of these two letters, I hope that that my hash function can distinguish between this key and this key, which is not the case if I just sum up the ASCII values. That's why I prefer to multiply each one by a different constant and then increasing the variabilities. Make sense? So let's see how it works in general. Let's assume that the size of my table M would be about 2 to the 20, more than 2 to the 16. It's about 1,000,000 cells in the table. I'm going to pick a set of random constant, A0, I forgot A1, sorry, A2, all the way up to AR. AR might be as long as the longest document that you have, but also practically it's not so bad if after 10 keys you started to go in a round robin. However, you are picking several of them, quite a few keys. The theory says each one should be picked completely separately. We'll talk a bit about what theoretical guarantees this method buys us. How do I generate these constants, all these AIs? Well, every AI by itself is picked individually as a number between 1 and m minus 1. Uniformly, each one of these numbers have the same probability to be picked, just called random variable generator. Okay, and this is how I generate this vector A. If you didn't do vector calculus, it's fine. Don't worry about it. I'm using the vector A just to generate, just to highlight that it's not one constant, but an order sequence of keys. I cared about the order and it's multiple numbers. That's all the only reason I'm adding the vector sign over here and make it boldface. Next, there is a key, something that I need to hash that just arrived. And I need to break it into characters, except that now I can pick every character to be a bit larger. I'll show you how I'm going to do it. I picked this wonderful key from the text return document that I thought that it will be interesting to hash. That tells you that according to section 1223, a non-profit organization, and that I just stopped copying. If that's my key, then I can break it into characters, but for efficiency, I can actually pick pairs of ASCII characters. So my first character will consist of the letter A and C. My next character will be C and O. My next character will be R and D, ing, that is according, now G and blank. Each character here has an ASCII value. So my key K, which is vector as well, consists of K0, K1, K2, K3, where K0 is just AZ, the beginning of the according. K1 is CO. Just go across, where is the camera? Just go along the string, go along the string, and take the first two characters, the next two, the next two, the next two, and so on. That's how you are creating the breakage of K into sub keys, K1, K2, K3. Each one you are assigning a numerical value. If you think about it as ASCII character, then K0, the first one, will be the ASCII character of A and the ASCII character of C, and I'm just multiplying it by 256. When you think about it as a stream of bits, then you have 1, 1, 1, 0, 1, 0, 1, 8 bits for the A. I'm not saying that that's the right one. 0, 1, 0, 1, 1, 1. That's the ASCII character of the C. And all you're doing is taking this number of 16 many bits, and this is K0. And then you keep reading the stream of bits from the file. The next 16 bits will be CO. The next 16 bits will be K2. Next 16 bits will be K3, etc. Finally, now when you understand how I generated all these numbers, K0, K1, dot, 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 until I'm done with the file, with the key, what is age of K? And I highlight here K depending on this constant that you decided about, A0, AR. How do I compute it? As simple as possible. Take K0, the first character, multiply by the first constant, takes the second key, K1, multiply by A1, take K2, multiply by A2, and so on and so forth. Sum it all up, it's a huge number, and do modulo M so you'll get a legit index and you're done. So it's just one pass on the file. So everything that I'm writing here on this slide is just generalization of everything that happened here in the BDCZ, except that here every character was actually what you know as ASCII character, so it's 8 bits. Well, in this example, I could be a bit more efficient, and every character should be of 16 bits. The rule of thumb right here should be that each AI and each KI should be small or equal than m-1. Just to get all the theoretical guarantees that we are going to say that it is a fantastic hash function. Make sense? So here, if I picked the hash table, wanted to take a reasonable practical example, your hash table has million cells. So million cells is more than 2 to the 16 many bits. So as long as both AIs and both the KIs were less than 2 to the 16, I am theoretically fine, and it's also very practical to do. One pass along the file and very simple operations. Everybody understands what's going on? How did I move from how did I move from the case that the key is one number to the case that the key is just a list of numbers? If I have a list of numbers, I need to accumulate them by a list of constants, but all I'm doing is multiply every number by its corresponding constant and sum it up. Okay. Questions? Mm-hmm. Because it might be 256. Wait, this 2 here is wrong. Right, it's 256 without, but I'm in base of 256, right? If I want to understand the what does the number 15 tells me? It is 5 plus 1 times 10 to the 1, because I'm in base 10 when I'm understanding 255. It's just the size of the ASCII. That's the number of characters that you have. I'm sorry? Oh, that's just a typo. Yeah. Yeah, it's just a typo from today, and it's just 255. But practically, all you do is thinking about this as a long list of 16 many bits and apply it as a binary number by itself. You never convert it to be characters and then from the characters making it bits as well. I just wanted to show how from the ASCII number I'm getting, from the ASCII characters I'm getting, I interpretate it as a number, but a relatively small number. Okay, we are done with a dot product. I'll give you several questions that a dot product will be the solution. Many examples at which you'll need it. It's really useful when you want to check, for example, do I have any 2 copies of an image? I have a lot of images that I stored in my computer. I want to see if one of these images appeared twice. I can compare every image to every other image. It's a bit slow. It's much faster to converge each one to a hash num value by itself, and then say, hey, if you have the same files that appear twice, then its hash value appears twice as well. So let's compare 2 files only if their hash values are the same. Right? And I'll let you figure out the details, but this type of operation as seeing if something exists on somebody else's database for good purposes or bad purposes, it's hashing really helps. Okay, let's talk about the other method of hashing, which is open addressing. That is resolved collision by open addressing, or as opposed to chain hashing. Chain hashing, every cell was a pointer to a linked list. A linked list, as I mentioned, are bad. Dynamic memory allocation, if you can avoid, do avoid. It makes it slower, it's not central, it's harder to debug, harder to optimize. If there is a way to avoid it, it's better. So, in general, in terms of actual constants, everything that you can do in an array, real array in C, not in Java, arrays is much faster than anything you can do with linked lists. But in terms of access time, even for operations, it takes a constant time in either data, in either structures. So open addressing, you might have seen it in 345. We are not going to use any storage outside the hash table itself, only using memory inside the hash table itself. That is, each cell could contain at most 1 key, A cell is either empty or it contains one key, one record. It's also a good place to store the rest of the details if you have other details together with a key. The same key, K, might be mapped to age K, but still it might be located in different location of the tables. So this sentence a bit contradicts itself. So we will have some schemes that will say, I think that I know where age of K is going to be, where K is going to be, but I might change my mind, depending on availability, because maybe somebody already lives in this cell and the cell is occupied. So when we either searching K or searching for a place for K for the purpose of insertion, we will have some method of checking where K is. We will have the first index that this particular K is, or the first index that will try to insert K, or the first place that we will search for K. Now, if it's either operation fails meaning if we search for and somebody else is there, then we didn't find it in this index. If you're trying to insert it, but the search is not empty, then the search is failed. Then we will have a second index for which we will try to search K or insert K. If this is not available, we will have the third, fourth, fifth, and so on and so forth. So now it makes our hash function a bit more complicated, because now my hash function takes two parameters. It needs to take K as before, the key. Maybe it's long, maybe it's short. I don't care about it. In these examples, I'll get back to Ks that are just individual numbers, but it might be strings as well. And I have another parameter I, where I is the trial number. Is this my first trial? Am I in my first try to search for this number K? Then I is 0. Is this my second trial? And that's I is 1. Is this my third trial? And then I is 2. Okay, so the same key to find where it is, I need to also know at which trial I am in my search or insert or delete process. That's a very highlight description. We desperately need examples. So to generate examples, I need to pick some concrete example of what age of K might be. So the rule as before, age of K takes a pair of keys. One is a key and one is a trial number, and my trial number will be a number between 0 all the way up to m-1. I will not have mth trial, never. The maximum number of trials that I'll have per key will be m-1. And the output will be, all from the hash function, will be a legit index in the table, that is a positive number between 0 and m-1. And let's take some examples. Age of Ki might be K plus I, all of it modulo m. That is the index plus the trial number modulo m, the size of the table. A different hash function would be K plus I times, and then I'll take a different hash function. Instead of just take I multiplied by 1, I'll multiply I by a different hash function of the K. We'll see why it's a good idea to use this type of hash function. Another example, age of Ki is K plus I square modulo m. Okay, and now I need to tell you how do I insert a new key. So let's take the first example, the simplest one, K plus I modulo m. What do I do? To insert a new K, I am in my first trial, so to confuse everybody, my first trial is index 0. I want to insert this new K into the table at index age of K, 0, because I'm in my first trial. If it's If the cell is empty, then that's where I'm inserting k. If the cell is occupied, then I'll check t of age of k comma 1. Compute k in 1, k plus 1 modulo m. Compute this index. If this is empty, then that's where I insert k. Otherwise, I'll try age of k comma 2, age of k comma 3, all the way up to age of k comma m, at which point I'll just give up and says the table is completely occupied, and I give up. There is no room in the table. What should be the finding algorithm? We first check what? The place that if I would insert k, what will be the first place that I'll try to check it? If I want to insert k, I'm inserting it into age of k comma 0. So the first place that I'll search for k would be the very same index, t of age of k comma 0. If it's empty, I will say no, k is not in the table. If I find somebody there, but it's not k, I'll say I have no idea and I need to try a different location. If I find k, then I stop. Right? If I find k, then that's where my search ends. If I did not find k, either because it's empty or because, if I did not find k because somebody else lives there, then I'll ask what is the next location that you'll insert k. It would be in age of k comma 1. Is k there? If yes, then you're done. If no, then check of age of k comma 2, age of k comma 3, until you try age of k comma m minus 1, and at this point you're done. And when do we stop? We also give up the moment that we landed on an empty cell, because if k was inserted, then that's a place that it should have been inserted. And I'm lying to you through my teeth, but we stop and give up and saying k is not there the moment that we landed on an empty cell. Example needed desperately. I want to insert 12, age of 12, I mean my first attempt, I equals 0. So that's my hash function. 12 plus 0 modulo 8 is 4. So I'm going to cell number 4 in the table. Nobody lives there, and that's where 12 is going to be inserted. Great. Inserting 15. My first trial is during the insert, I equals 0. So age of 15 and trial 0 is 7. 15 modulo 0 is 7. So 15 is inserted in cell number 7. Okay. Insert 20. Age of 20 comma 0 is 4. So that will be where I want to insert 20, but somebody is living there. So my trial 0 failed, and I'm going to move to trial 1, my second trial. Age of k equal 20, second trial, that is I equal 1, is k plus I, 21 modulo 8, which is 5. So 20, my first attempt will be in cell number 5, which is indeed empty. So that's where 20 is going to be inserted. Insert 23, going to cell 7, collision. My second trial, what is 23 plus 1, 24, all of it modulo 8, will be 0. So that's where 23 is going to be inserted. Insert of 28. 28 will try to be inserted here. Collision. So it will be inserted right here. And now let's go to this table and let's see how after this all this sequence of insertions. Any questions so far about the insertions? Everybody is good with the insertions? Let's just show how do I do search. I want to do a search of 28, age of 28, and attempt 0 is 4. That is my first attempt to look for 28 is in this cell, because that's where I would try to put 28. Somebody else is there. Then I'll move to the next cell. That's my second attempt to search for 28, because once again, that's where 28 would have, that's a sequence of insertions that I'll do. I'll move to the next cell. Not 28 as well, 28, which I find at this point, and I'm happy. So 28 was successful. Search for 16, age of 16 is 0, taking me to this cell, not 16. Moving to the next cell, because it's k plus I. This cell is empty, so I conclude that 15 is not in the table, so I'm done. 16 is not in the table, and I report that, and I report that 16 is not in the table. Okay, so that's how I'm doing it, except that I'm a bit lying, because what should I do if I'll delete somebody? That will be interesting. We'll talk about it next class. Good. Questions, anybody? Thanks.